On December 6, 1917, as the First World War was drawing to a slow but inevitable conclusion, the residents of Halifax, Nova Scotia, thousands of miles from any meaningful conflict, were awakened to an explosion. Not just any explosion, but the largest non-nuclear man-made explosion in the history of humankind. It would require a generation of thought and a Second World War before such a large force would be released by man again. A French cargo ship, the Mont Blanc, had collided with an empty Norwegian cargo ship on its way to New York to take on war supplies for the Allied forces. But the Mont Blanc was not empty. She carried in her a belly full of explosives ready for use by Allied forces in Europe, including the chemical compounds trinitrotoluene, picric acid, and gun cotton. When struck, the Mont Blanc caught fire and her fate was sealed nearly instantly. Just 20 minutes after the fire broke out, her cargo underwent a violent chemical reaction, one of truly historical proportions. Nearly 2,000 innocent lives were lost, and every major structure for 1.6 miles in all directions from the bay was damaged or destroyed as a shockwave rippled through that community. Temperatures near the source of the disturbance reached those that one might experience at the surface of the sun, and the pressure wave that rippled outward was on par with the pressure that a vessel would experience at the bottom of the Mariana Trench, the deepest ocean floor in the world. The residents of Halifax had just experienced what chemists call a detonation, a chemical reaction so violent and rapid that it creates a shock wave of energy that exceeds the speed of sound. And this was not just any detonation, but a historically powerful one. In this lecture, we will endeavor to understand what happened at the molecular level on that fateful day in 1917, and to use that knowledge to better understand one of the most influential chemical inventions of all time: explosives. We just finished a discussion on the topic of fuels, materials which, when paired with an oxidizer and exposed to an ignition source, can release heat and do work over time. But a sharp student might have already asked the question, if one compound can be oxidized by another, is it possible for a compound to oxidize itself? Can a molecule self-destruct by this kind of reaction? The answer is yes, and sometimes with devastating consequences. But before we get to those consequences, let's try to understand a bit about how conventional explosives were discovered and how they've impacted human history. Now remember, there's oxygen in the air all around us, so we're always going to have oxidizer present. And I'm going to provide a source of ignition to each of these balloons using a flame. Now let's see what happens depending upon which mixture of gases or pure gas I have in the balloons above me. I'm going to put my ear protection on, just for safety here. We're going to begin by bringing an ignition source next to a balloon filled with helium, which is an inert gas. So we'll have oxygen and we'll have ignition, but we're not going to have a fuel. As you can see, I merely succeeded in popping the balloon. There was really no chemical explosion that went on during that process because we're missing one of the three crucial ingredients. Next, let's do the hydrogen balloon. Now in this case, we have pure hydrogen surrounded by the oxidizer oxygen and of course the flame. So we're going to have all three ingredients present. Let's see what happens. Great. We got an explosion that time because we had a fuel, we had an oxidizer, and I provided an ignition source. But there's more to obtaining the most forceful explosion possible than simply combining these three ingredients. They have to be combined in the most thoughtful and appropriate way. Let me demonstrate that to you using the third balloon, which contains a mixture of hydrogen and oxygen inside the balloon. So those gases are very closely mixed together. My oxidizer and my fuel are no longer separate and have to mix during the reaction, but instead they're pre-mixed. So let's get that ignition source up there and bring the third ingredient in and see what happens. As you can see, we got a much more forceful explosion using the same fuel, the same oxidizer, and the same type of ignition source. The reason we got a better explosion is because we had our fuel and our oxidizers mixed together very, very well so they could react as rapidly as possible. And it's this context, this principle of mixing fuel and oxidizer that's going to be the overriding story in our lecture. The chemical reaction that drives gunpowder explosions, specifically black powder explosions, is this one. It's carbon with potassium nitrate and a little bit of sulfur to alter the reaction a bit, to lower the energy needed to get it to go. Now, that's not a catalyst, because notice that the sulfur is reacting. So we wouldn't call this a catalyst, even though it's really added to lower the energy needed to start the reaction. But let's think for a bit about the thermodynamics of a gunpowder detonation using this reaction. Now, the standard enthalpies of formation for all of these species are as follows. We have elemental nitrogen in the gas phase, sulfur, which I've written as S, but we could just as easily write as 1/8 S8, which is its standard state, and 3 moles of solid carbon, also its standard state. So all of these will have 0 kilojoule per mole enthalpy of formation. But my other species will not. My potassium nitrate has an enthalpy of formation of negative 493. My carbon dioxide of negative 393 kilojoules per mole, and my potassium sulfide of negative 406 kilojoules per mole. So let's use these numbers and see if we can determine whether this reaction should be exothermic or not. Now, in order to do this, I can first neglect all of my elements because they are 0 kilojoules per mole. That's going to simplify things dramatically. And I'm going to use my calculation for the free energy of a process, applying Hess's law, using the free energy of all of my products, taking the sum of that, subtracting from that the heat of formation of all of my reactants, getting an ultimate value of negative 599 kilojoules. So in this case, when 3 moles of carbon is mixed into a black powder mixture and then combusted, I can expect to liberate about 600 kilojoules worth of heat. Now that we're done with that, let's think a little bit about the entropy of this reaction. You'll notice that on my starting material side, I have all solids, whereas in my product side, I have a considerable amount of gases. That means that this reaction is not only enthalpically favored, but it's also entropically favored, producing a large amount of gas from all solid materials. In fact, that 4 moles of gas from the same amount of black powder that released that 600 kilojoules of heat at standard temperatures would expand to 89.6 liters. And when we consider the amount of material in my reaction up here, what we find is that you get about 1/3 of a liter of gas per gram of gunpowder that's detonated when you do so under standard temperature conditions, keeping in mind that the temperatures are actually quite elevated because of the heat released. So this allows us to see how gunpowder works so effectively at causing the kinds of explosions that it does. Add to this energy release the fact that it happens very quickly, and that all solid ingredients react to form carbon dioxide and nitrogen gases, which cause expansion, and you have one very hot, forceful expansion as a result of this reaction. This force is adequate to propel rockets across the sky or musket balls across a battlefield, and it remained the method of choice for this purpose from the time of its invention until the late 1800s. Black powder, though ingenious for its time, still technically requires the mixing of a fuel and an oxidizer. Of course, both are in the solid phase, so grinding them together to a fine powder can make for one very fast reaction and release of energy. But no amount of grinding can mix fuel and oxidizer as closely together as chemically bonding them to one another can. And although it took some time, about 8 centuries after gunpowder's development, a technique for this was eventually found. Credit for the discovery often goes to Christian Friedrich Schönbein. Now, Schönbein is yet another in a great line of famous chemists who turned a terrible accident or failure into a positive research experience. See, about a decade earlier, it had been realized that mixing the cellulose from wood with nitric acid formed some remarkably flammable products. Schönbein was continuing this work in, of all places, his own kitchen in 1845. One day, while his wife was away, he was experimenting with nitric acid and he had a spill. Now, gentlemen, imagine that you're Friedrich Schönbein. We don't need to know anything about his wife. Any wife would be furious if you spill nitric acid in her kitchen. So what do? Of course, you wipe up the mess with anything that doesn't belong to your wife. Please do not compound your folly here. Leave her dish towels out of this. So in Schoenbein's case, he decided on his own lab apron instead. Now with the mess cleaned up, he set about doing what any good husband would do in this situation, concealing the evidence. Of course, we got to dry that apron off, don't we? And what better place to dry a damp apron than next to the stove? But Schoenbein's plan backfired in a very literal sense, when his apron suddenly and spontaneously burst into flames under the heat of the stove on which he had attempted to dry it. Schoenbein had unwittingly discovered that the same effect that had been observed using the dense cellulose of wood a decade earlier was amplified when the lighter cotton fiber, made of the same cellulose material, was substituted. The resulting compound was called gun cotton, and it combusted with remarkable vigor. But why? Gun cotton's chemical name is nitrocellulose, and it looks a bit like this. I've created just a few units of it here so that we can look at its structure. Now you notice that we have the cellulose backbone here. I've got just a few sugar rings, but that all along there, and I've removed the hydrogens as well, but all along that backbone there you can see where these so-called nitrate ester groups have been substituted. So we've chemically attached all the oxygen that we need to have a good vigorous combustion reaction. But let's take a closer look at those nitrate ester groups and see if we can understand why they make the molecule so unstable. Well, in order to do this, we have to think of them in terms of their Lewis structure. So I've taken just a snippet of that molecule, and we're going to look at the Lewis structure of that piece. Here it is. This is the nitrate ester functional group as a Lewis structure. And you may notice that I'm having some problems here. I've drawn this as a structure with a positive charge on a nitrogen and a negative charge on one of the two oxygens. Now, normally we would strive to find a way to get those two charges to cancel out. But there is simply no way that we can do it without violating the octet rule. So this is the best possible Lewis structure for a nitrate ester. And you may also notice that I can draw a resonance contributor in which the negative charge is on the other oxygen, meaning that in my overall picture of this functional group, a resonance hybrid, I expect to see partial negative charges on my oxygens and a full positive formal charge on my nitrogen in the middle. Now, that makes all of these atoms very unhappy, and they would much, much rather react to become some of our more stable characters from the course, things like nitrogen gas and carbon dioxide. And that is, in fact, what they do given the first chance. Now, I'd like you to notice that when we combust 2 units of our nitrocellulose, we get some really interesting products here. We get 9 moles of carbon monoxide, 3 moles of carbon dioxide, 7 moles of water, and 3 moles of nitrogen gas. Now, when we analyze the products that we get during the combustion of nitrocellulose, take a look at what happens. Here are my 2 units of nitrocellulose, and they break down to form nitrogen gas, water, and carbon dioxide, all the model of stability, very, very stable compounds that release lots of energy when they form. But there's a problem. Look at this. I've got 9 moles of carbon monoxide gas forming as well. Nitrocellulose simply does not have enough oxygen to finish the job. As a result, it doesn't release quite as much energy as it could. So, although this is a wonderful self-combusting material, it's not optimized yet. Now, the cleaner burning nature and easy synthesis of gun cotton caused it to quickly replace gunpowder in most firearms applications. But the quest for a fully self-oxidizing compound continued, and it wasn't long before another chemist, this time an Italian named Ascanio Sobrero, produced the first completely self-oxidizing compound. Sobrero took a page from Schoenbein's book, using nitric acid to convert another compound into an explosive of legendary power. Now, Sobrero used glycerin, a readily available material that's a byproduct of the soap-making process. So here it is, glycerin. And what he did was he added some nitric acid to his glycerin to create a very familiar compound to us all, nitroglycerin. Now, in this particular reaction, the glycerin molecule reacts with nitric acid in a condensation reaction to form water. So here my 3 moles of nitric acid are going to react with the glycerin, expelling some water, and creating nitroglycerin. And this particular compound has got loads and loads of oxygen. In fact, it's got enough oxygen to completely get that job done of self-oxidizing. Now, if you go to look for reactions of the total self-combustion or self-oxidation of nitroglycerin, you'll find a number of different depictions of the reaction. Sometimes it will be for 1 mole with some byproducts that involve mixtures of hydrogen, nitrogen, and oxygen. Other times you'll see it balanced with 4 moles to try to get better balance. And my particular favorite is this one here. All of these are valid representations of the kinds of reactions that go on, but this one is the best in my opinion because it shows 2 important things. The first is there's no carbon monoxide left. In this case, nitroglycerin has oxidized completely. In fact, it's oxidized so completely that the other feature that I think is interesting is this. There's actually a little bit of oxygen left over. It's got all that it needs and more to release all of the chemical potential energy stored inside. This is what makes nitroglycerin such an effective and potent explosive. Sobrero found nitroglycerin to be highly unstable. In its pure state, it could be made to detonate by the heat generated by a single candle or a physical shock as mild as dropping a container from a lab bench to the floor. Sobrero became a vocal critic of his own creation, feeling that the incredible destructive power of his discovery, coupled with how easy it was to set off, made it at worst impossible and at best irresponsible to try to use it. But a contemporary of his felt differently. His contemporary was none other than the now world-famous Alfred Nobel. Nobel, the son of an engineer and explosives entrepreneur, had a distinct interest in explosives, and his father's success meant that Alfred was free to follow his interests in chemistry. His interests took him to Turin, Italy, where he found himself studying alongside none other than Ascanio Sobrero. Nobel, having grown up in the shadow of a father who was an explosives expert, didn't share Sobrero's grim outlook on the future of nitroglycerin. He instead worked to find a way to stabilize nitroglycerin, making it safer to transport and set up before releasing its awesome destructive force. He discovered that he could use a mineral compound called diatomaceous earth, an inert, crumbly, powder-like material that the liquid could adhere to. And this created a more stable material that could be fashioned into sticks and wrapped in paper to create a product that would not detonate if dropped or left in the sun. It delivered no less energy when it was detonated, but it simply required a stronger shock to do so. Nobel proved to be a prolific inventor and businessman, developing a blasting cap, a special detonator used to deliver that shock to his dynamite. This and 354 other patents made Nobel a very wealthy man by the time of his death in 1896. But despite the apparent fearlessness and opportunism that drove him to create this explosive, there is evidence that Nobel suffered from a crisis of conscience over his creation. Even as he worked to develop dynamite and safer ways to use it, both dynamite and nitroglycerin were responsible for many deadly accidents. This earned Nobel a reputation in many circles as an opportunist who placed personal gain ahead of public safety. Many believe that it was his guilt over these effects of his product and his desire to salvage his family's good name that Nobel made a change to his will late in life, donating the vast majority of his fortune to endow the Nobel Prize. His creation has endured for more than a century, becoming what is arguably the most distinguished award that a chemist can receive. Yet another popular explosive from that era was picric acid. Picric acid is a compound synthesized by reacting a compound called phenol, easily extracted from coal tar, with nitric and sulfuric acids. The product of this reaction is picric acid, an extremely powerful and very shock-sensitive reagent. Not too surprising when we compare its structure to that of nitroglycerin, is it? We see some very similar looking functional groups on these molecules. But picric acid is a larger molecule, and it exists as a solid at room temperature. And that solid, when kept dry, explodes just like nitroglycerin at the slightest shock. Picric acid was the explosive of choice in World War I, and it was the material responsible for the detonation in Halifax, Nova Scotia that wrought so much havoc. It's a chemical cousin of one of the world's most famous explosives, TNT, or trinitral-toluene. TNT's history is quite unusual. It was first synthesized in the 1860s, and TNT was used primarily then as a dye because of its attractive yellow color. It was not until 2 decades later that its explosive properties were fully understood and explored. Now, TNT has 2 very important differences when compared to picric acid. First, it's a bit tougher to detonate, which makes TNT compared to picric acid in much the same way that dynamite does to nitroglycerin. Now, second, the substitution of a methyl group for the hydroxyl of the picric acid makes TNT unable to hydrogen bond to other TNT molecules. Now, as you might expect, this lowers the melting point of TNT in comparison to picric acid. So TNT can be melted down easily and poured into artillery shells in a much safer liquid form than picric acid. TNT was adopted by the German military prior to World War I, and it had striking results. In a bit of a counterintuitive twist, the greater resistance to detonation made TNT a more damaging weapon. Shells that were filled with TNT had that extra fraction of a second to penetrate armor before exploding, whereas shells using picric acid tended to explode instantaneously on the slightest contact with their target. Now, these favorable characteristics of TNT, though not recognized immediately by all nations, have since made it an ordnance of choice for militaries around the world. So far, we've discussed probably the 2 most common phases for explosives. Some are liquids, like nitroglycerin. Others are solids, like gunpowder, gun cotton, picric acid. But what about so-called plastic explosives? Most of us tend to think of them as relatively new arrivals to the explosives world, an example of modern technology at work. They've been made famous by Hollywood, which depicts their use in countless films as a lethal tactical tool used by clandestine military forces on critical missions. Now, plastic explosives are most simply defined as explosive materials which are moldable. They're particularly useful in demolitions applications because their soft form allows them to be very precisely placed and shaped to effect maximum destruction with minimum explosive power. Now, although plastic explosives like the famous C4 used by militaries and even terror organizations across the globe are relatively recent inventions, it might surprise you to hear that their history reaches back more than a century, all the way to Alfred Nobel. Nobel always struggled with a serious problem with dynamite. Liquid nitroglycerin would sweat out of the dynamite over time, and this would lead to potentially deadly pools of nitroglycerin forming in crates of his high explosives. In light of this problem, Nobel started to seek out new materials to replace the diatomaceous earth that he had originally used to produce dynamite. And Nobel had an idea. What if he could use an absorbent that wasn't inert, but explosive in its own right, stabilizing the nitroglycerin, but keeping that explosive power maximized? Of course, he turned to one of the only simple solid explosives of his day, gun cotton. In 1875, he perfected his recipe, creating a sort of explosive gel comprised of nitroglycerin, gun cotton, wood pulp, and a few other ingredients. The resulting product was a gelatin-like substance with explosive power greater than nitroglycerin itself, but with greater stability, less propensity to sweat nitroglycerin, and as a bonus, it was easily moldable into the needed shape at the time of use. Now, more modern versions of plastic explosives have a more obvious connection to their name. C4, for example, does in fact contain plastic. Just a small amount, though. C4 consists of about 2 to 3% polyisobutylene, an addition homopolymer that also has been used as a base for chewing gum. The difference between C4 and chewing gum is that instead of being mixed with colors and flavoring, the polyisobutylene in C4 is instead laced with a massive amount of a compound called 1,3,5, trinitropyrhydro-1,3,5-triazine, more commonly called Research Development Explosive, or RDX for short. Again, if we take a close look at its structure for RDX, we see stability-stealing formal charges on nitrogen and oxygen in abundance, making a self-oxidizing compound with highly explosive properties. And by now you're probably beginning to notice a certain theme that's common among most chemical explosives. From gunpowder to dynamite to TNT to RDX, All of these compounds contain significant amounts of nitrogen. This is no coincidence. And in fact, it was the driving force behind the development of the famous Haber-Bosch process that fixes atmospheric nitrogen, or N2, creating ammonia, or NH3. You might recall that diatomic nitrogen, the likes of which we find in the atmosphere, is exceedingly stable due to its triple bond. Each nitrogen atom also naturally has an oxidation state of 0 in this molecule since it's bonded to another nitrogen atom. But now take a look at ammonia. In this molecule, nitrogen has an oxidation number of -3. Since the less electronegative hydrogen atoms each take a +1. Now, this requires a great deal of energy input, as Haber himself found out when designing his high-pressure, high-temperature reactors that are used to make it. So ammonia is less stable than diatomic nitrogen. But so far, all of the examples that we've discussed didn't contain nitrogen in this oxidation state. Quite the contrary. In most of the explosives that we've considered, nitrogen was bonded not to hydrogen, but to oxygen, either as a nitrate ion, as in saltpeter, an ingredient in gunpowder, or as a nitro group, as in gun cotton, nitroglycerin, and TNT. So Haber took care of the hard part, producing fixed nitrogen. But to make an explosive requires some additional chemistry. The nitrogen in ammonia needs to be oxidized, essentially combusted in the presence of oxygen. The way that we go about using nitrogen in explosives design primarily is this. The Haber process, of course, gives us a very easy reaction to run, if not a cheap one, to create as much ammonia as we may need. But remember, most of our explosives contain things like nitrate esters and nitrate groups. They have lots and lots of oxygen, and we haven't yet covered how we get that oxygen into the equation. The way that this is done is the ammonia is reacted with oxygen in a several-step process involving combustion and solution phase reactions. But the ultimate product of that is nitrogen dioxide. Now, this NO2 serves as a starting material in the synthesis of that very important nitric acid, which always seems to be part of the equation in explosive synthesis. That nonmetal oxide, NO2, can be hydrated to form HNO3, nitric acid. And also, as it turns out, a little bit of NO, nitrogen monoxide, which can then be recombusted in oxygen to be re-entered into the process here in the second step. Now, this is how we get the type of nitrogen that we really need to create a very powerful explosive. And it's illustrated very easily when we think about not only nitric acid, but ammonia as well. So here's a molecule of ammonia and a molecule of nitric acid. Now, you'll notice if you run the numbers that the formal charges on these are drastically different. By fully oxidizing our ammonia, we get nitric acid where there's a +5 formal charge on nitrogen, as opposed to over here on ammonia where there's a -3. Now, that means that they are relatively unstable, and when brought into contact with one another can become very, very reactive. In this case, when we bring ammonia and nitric acid together, the first reaction is not an explosion. The first reaction is a simple proton transfer in which we get an ammonium ion and a nitrate ion. And they, of course, form a familiar ionic compound, ammonium nitrate. Excellent for use in fertilization, also potentially excellent for use in bomb making. And that's because the nitrogens in these compounds are so drastically different in their chemical environments. As soon as they have an opportunity to lose those formal charges and become nitrogen gas, they will. This is what drives many of the explosives that are used even today. Because the same mix of compounds is used as a fertilizer in agriculture, this reaction between ammonium and nitrate has been behind some of the most catastrophic industrial accidents in human history, like the West Texas Fertilizer Company explosion in 2013, which claimed 15 lives and leveled nearly 100 buildings around the plant. The somewhat easy availability of this mixture for farming purposes made it accessible to those who wished to do harm as well, like Timothy McVeigh, who used this chemical concoction to carry out the Oklahoma City bombing of 1995. At the time, that was the deadliest act of domestic terrorism that had ever been carried out in the United States. Now, anyone who's been through an American airport in the past decade has almost certainly either witnessed or themselves been the subject of a curious test performed by the Transportation Safety Administration personnel. An alcohol swab is wiped across baggage or other personal items, then inserted into a device which, hopefully, gives you the go-ahead to allow you through to the terminal. Now, just what are those devices and what are they looking for? Well, the answer is they're mass spectrometers. They're highly sensitive versions of the device built by J.J. Thomson to study the structure of the atom in the early 1900s. These devices analyze vapors emitting from the swab by ionizing them and then accelerating them through a magnetic field, watching closely for ions that behave like bomb-making compounds. A modern mass spectrometer can detect those ions at the parts per billion level, making even the amount of residue transferred while creating or packaging a bomb easily detectable. Now, one downside to this technique is that certain bomb-making components, most notably glycerin, used in the manufacture of dynamite, are also used in household products like hand lotions and soaps. Recall also that nitrates have an even longer history of being used in medicines, most notably heart medications. Now, so sensitive is this technique that it can sometimes detect the residue of these types of medications. So, false positive results are sometimes registered in these tests, making them only a primary screening tool. Anyone unfortunate enough to smudge the wrong mixture of hand lotion on their baggage or have the misfortune of having just applied a heart medication patch or pill might be treated to a secondary screening before they're permitted to move on. So let's sum up today's lecture. We started by considering what takes an energy-producing reaction and promotes a material from a simple fuel to an explosive. Now, the answer was that the combustion or decomposition has to be rapid and generate expansion fast enough to exceed the speed of sound and create a shock wave. Then we saw how the quest for a cleaner explosive led to experiments with nitric acid and cellulose, ultimately leading to the creation of the first self-oxidizing explosive, nitrous cellulose, or gun cotton, invented by Friedrich Schönbein, at the cost of his lab apron and probably a pretty good scolding from his wife. But gun cotton was not optimized for self-combustion. And next we saw how Ascanio Sobrero succeeded in creating nitroglycerin, a compound perfectly balanced for total self-oxidation. Next we saw how Alfred Nobel, an ambitious young scientist and businessman from a family in the explosives business, found a way to stabilize nitroglycerin using diatomaceous earth to create dynamite. This made an easier to use but no less deadly explosive that earned him a reputation so dubious that he established the world's most famous philanthropic prize in an attempt to repair his legacy. Next, we discussed the idea of plastic explosives, an idea almost as old as dynamite itself, but elevated by modern technology to be one of the most effective tactical and demolitions explosives available today. And finally, we paused to think about some of the common features to many of these explosives, and in how authorities, not just in the US, but all around the world, try to use these commonalities to develop screening techniques to ensure the safety of all travelers. Over this course so far, and particularly in the last few lectures, we've examined some of man's most influential chemical inventions, from refrigerants to weapons to medications, from fuels to explosives to engineered materials like rubber. But as usual, there are always unintended consequences to tinkering with the world around us at the molecular level. So the next few lectures, we're going to turn our attention to the greatest chemistry lab of them all, our environment. We're about to start our final journey of the course, one that will take us from the bottom of the ocean to the core of the Earth, to the outer reaches of the atmosphere, and ultimately into the depths of the cosmos.